So hello, welcome back to our turbulence modeling series, and we're going to continue the Spalart Allmaras Model. Okay, so basically in the last video we stopped here and we said that we needed these trip terms, in our Spalart Allmaras Model, to artificially reduce both our production and destruction terms over here so as to ensure numerical stability. So this is just tweaking for numerical stability. All right. Now the problem when you do this, trip terms, now the thing is the transition from laminar to turbulent layer is not smooth, because now you artificially alter these terms. You will also need to ensure that you need to compensate for the missing terms by increasing the turbulence viscosity just enough in the what do you call that, transition layer and onwards. Okay, so like I said, we sort of kaboomed our boundary layer source. Okay, mu tilde source and destruction terms. Remember, nu tilde is actually the turbulence viscosity in the log law region and the bulk region. Okay, so by doing the above, so the above is these trip terms. Okay, ft2. Okay, this ft2 is the main thing we did, and remember ft2 looks like this. It's an exponential term, so it dampens away from it dampens at the wall. Okay, let's see. Yeah, so here we are again, the trip terms, and okay, great. So now we need to offset. Now that we offset these two terms in the boundary layer region, we need to ensure that there's enough turbulence viscosity in the boundary layer. So again, this is a numerical stability thing. And we see this extra term. We see an extra term popping up. Okay, the extra term is let's see, yeah, ft1 delta u squared. All right, so ft1, so this is a trip term also, delta u squared. So this term here actually helps you to transition from the laminar region, because you just destroyed all the turbulence in the viscous sublayer and some other regions as well, maybe the buffer layer as well, so as to ensure numerical stability. But you kind of need to generate enough turbulence in the transition region, which is okay over here. Here's the viscous sublayer region, which I will box in purple. And then in between you have the transition region, where you have your transition from the laminar regime. Here's a laminar because it's viscous sublayer, to the turbulent regime, which the log law region and the outer region mainly do. All right, so this is where we need to compensate for this addition we have to our numerical instability thing. So first thing first, what is delta U? So delta U is the norm of the difference between the trip point and the point we are calculating. So what is this trying to say? So let's say your trip function happens here, somewhere in the turbulent transition regime. All right, so you kind of measure the velocity here. So this is the U at the trip point, and then let's say you are calculating somewhere, you are calculating a velocity here. You are calculating a velocity here, and that is your that is the velocity at wherever you are considering. So this is actually a reference velocity, and okay, this is actually a reference velocity. So if you were to do a vector like subtraction, so you'll do something like this. Okay, you'll do a vector subtraction like this to do a difference, and let's say you want the magnitude, right? Magnitude. okay, what would you do? So if you have a vector and you wanted the magnitude, so let's say x1 equals to, okay, or x bar, or the vector x equals to x1, x2, x3. Yeah, so if you wanted the magnitude, you just do this, x1 squared plus x2 squared plus x3 squared, and this is the length, so to speak, the length of this vector over here. Okay, so another more complicated way, this is also called the norm of a vector. This is more complicated way of saying it, or the more mathematical way of saying it, and you can find it on Wolfram Mathematica here. The norm of an object is usually is a very abstract way of describing the length, size, or extent of an object. So if you don't say, look at this part, it says most commonly the unqualified term norm means to say if someone mentions the word norm without any other like specification, it refers to the flavor of the vector, or another bombastic term there, and it's more technically known as the L2 norm. And this is very important. What it means is that it gives the so-called length of the vector. So what I just talked about here, this norm of a vector is actually called the L2 norm, and it's probably what this norm is talking about here. Okay, this is the norm of the vector, and this is delta U is the norm of the difference between the velocity of the trip and that of the field point we are considering. So this is what it is. This is actually the magnitude of the velocity difference. So if we were to apply this to this over here, this would just be the magnitude of velocity difference. Alright, because it shows you that so-called length of the vector. And that's what the norm is about. It's the L2 norm, which is the magnitude of velocity difference, which they rightly use the term delta U because that's actually the difference in velocity. So hopefully that clarifies what this difference in velocity is. Okay, so here are some references, just ignore that. Now what does FD1 look like? So FT1 is defined over here. It's very long, okay, but let's go through term by term. FT1 equals to CT1, so these are trip terms again, GT, which is a function, and then it's some exponential of minus CT2 minus CT2 times omega t squared divided by delta U squared. Okay, so you have d, which is the distance from the wall, plus gt squared again, and then into dt squared. So there are some terms we're probably not sure with. First thing, let's deal with gt. So gt is defined as the minimum of 0.1. Alright, delta U divided by omega t delta xt. Omega t delta xt. So what is delta xt? Delta xt is the grid spacing along the wall at trip. So delta xt equals grid spacing along wall at trip. I'll just leave it as it is, not too much explaining, not going to explain too much there. let's go into omega t next. What is omega t? Omega t is actually over here. Omega t is the vorticity of the wall at the trip point. Okay, so omega t equals the vorticity of wall at trip point. So remember, we are talking about the trip point here. The trip point is like, for example here, the trip point, the reference point, the trip point, it's over here. And we want the vorticity, which is the curl equivalent of the curl of the velocity at the trip point. So nabla times, so this is the curl, u vector at the trip. So curl of the velocity at the trip, that is what this omega t is. So don't worry too much about that. So this is the curl. And what is dt? Let's take a look. So dt is stated here. We also introduce dt, the distance from the field point to the closest trip point or line. So it's the closest distance from, let's say, here to, because I mean, in a 3D plot, so to speak, there will be a turbulent transition region over here. Okay, this is getting a bit messy. It's very hard to see it now. There's too many lines there. All right. So let's go here and remember. Okay, let's say we have a velocity profile again. Okay, I'll just leave it as the line here. So remember, you have a viscous sublayer, you have a transition. Okay, viscous sublayer, transition, log wall, outer, and then you have the bulk. So let's say your trip point is somewhere here. This is where you have your transition, and let's say you have a point you're considering somewhere along this 2D line, right? So this is the x, this is the y. So you try and have a distance measurement here. So delta d to the closest trip point. All right, the closest trip point. So there are many trip points along this along the xy axis, so to speak, because this, when you join these points, it will basically tell you, okay, here's laminar, and here, laminar plus transition, and here's the fully turbulent region. Okay, so here's a fully turbulent region where you don't want to worry about all this numerical instability stuff. So dt, d is the distance from the wall, dt is the distance to the closest trip point. So if you are here, the closest trip point will be, let's say here. You will find the closest trip point there. Okay, so that's what dt is. So this ft1 will go into here. All right. So yeah. So the log law region is where our turbulent boundary layer will be. That's where you will have your usually you will start to have your transition somewhere here, or that's where your trip point will be to try and start kicking in the numerical stability things. The viscous sublayer is the laminar boundary layer. The buffer zone is actually this transition region, which you can, take a look at this internet book on fluid dynamics, the law of the wall. That will tell you more on that. Okay, so this is more about the norm, and where you can find that is a Wolfram. Okay, so yeah. So in this, so this delta U is the difference using this norm. So this serves as a term to build up the turbulence somewhat in this transition zone, just before the trip starts to kick in. And because after the trip kicks in, you don't really need this anymore. So you need to artificially build up turbulence here in the transition region, and I think that's what this this term is here for. Because when you artificially destroy these two terms in the trip zone, where you have all this transition stuff happening, you need to artificially increase nu tilde so as to have the correct velocity profile. So yeah, that's it. The end product is like this. Okay, the end product is like this, and if you take a look at the Spalart Allmaras model, you'll see exactly the same terms. These transport terms and the convection term and the time dependent term, the substantial derivative. You see chi again, you see FV1, you see nu t and nu tilde. All these things are stated over here. So hopefully that gives you a good overview of the Spalart Allmaras model, and it makes you more comfortable to use it. And yeah, it's very simple to construct, and basically, there's not too much more functions you have to think of because it's already built into the model. So you can just set I mean, if you are actually doing an actual simulation of a boundary layer flow where you have some u infinity here, all you have to do is to set nu tilde equals to 0 at the wall here. I think more or less you are pretty much okay. So yes, nu tilde should be 0 at the wall, and I think that's how you set your boundary conditions. I may have to check, but yeah, this is why this equation looks so complicated. It's because all the wall functions are already built into this transport equation, and you don't have to think about it anymore. So yeah, that's the Spalart Allmaras model for you, how it's being derived and constructed, and that's how you go. So thanks for watching. I'll see you guys next time. Bye bye.